Step outside on a clear night, away from the glow of streetlights, and let your eyes adjust to the darkness. Above you, thousands of stars pierce the velvet sky like tiny diamonds scattered across black silk. They appear so still, so eternal, as if they've hung in exactly these positions since the beginning of time. Your ancestors looked up at these same constellations, finding comfort in their apparent permanence, their steady presence through countless generations. But tonight, as you rest beneath this cosmic canopy, you're about to discover that nothing could be further from the truth. The universe above you is not still at all. It's moving, stretching, expanding in ways so subtle and vast that human eyes cannot perceive the motion directly. Every star you see, every galaxy beyond your vision, every point of light scattered across the cosmic darkness, all of it is part of a grand dance of expansion that has been unfolding for nearly 14 billion years. This expansion isn't like a balloon inflating, with galaxies moving through space like ships sailing across an ocean. No, something far more mysterious is happening. Space itself, the very stage upon which all cosmic drama unfolds, is growing larger. The distances between galaxies are increasing not because they're racing away from each other, but because new space is being created in the gaps between them, like invisible hands gently stretching the fabric of reality itself. And here's where the mystery deepens into something almost magical. This expansion, which should be slowing down over time like a ball thrown into the air that eventually falls back to Earth, is actually speeding up. Something is pushing against gravity's embrace, something that makes up nearly 3/4 of all the energy in the universe, yet remains completely invisible to us. Scientists call this mysterious force dark energy, though the name itself admits our profound ignorance about what it actually is. Imagine lying in a meadow on a summer evening, feeling the earth solid beneath your back, while the sky opens endlessly above you. You might think of space as empty, as nothing more than the absence of things. But space is alive with this mysterious energy. Every cubic centimeter of the seemingly empty void around you contains a tiny amount of dark energy so small that a trillion measurements couldn't detect it in your backyard. Yet, when you add up all the space in the observable universe, this whisper-quiet energy becomes the dominant force shaping cosmic destiny. The stars above you seem so peaceful, so unchanged from night to night, that it's hard to imagine they're heart of this vast expansion. The light reaching your eyes tonight left some of those stars years ago, decades ago, even centuries ago. That gentle starlight carries within it the history of cosmic expansion. Though you need sophisticated instruments and years of careful observation to read the story it tells, think of the most distant galaxies, so far away that their light has been traveling toward us since the universe was young. By the time their ancient photons reach our telescopes, space has expanded so much that the light itself has been stretched, its wavelength pulled longer like a piece of elastic band being gently extended. This stretching shifts the light toward the red end of the spectrum, creating what astronomers call redshift, a cosmic signature of expansion, and in the very light that crosses the universe to reach us. As you lie here, contemplating the night sky, you're witnessing something unprecedented in the history of cosmic thought. For most of human existence, people believed the universe was static, unchanging, eternal in its current form. Even Einstein, when he first formulated his equations describing the structure of spacetime, assumed the universe was neither expanding nor contracting. He added a mathematical term to his equations, something he called the cosmological constant, to keep the universe perfectly balanced, neither growing nor shrinking. But the universe had other plans. Within decades of Einstein's work, astronomers began discovering that distant galaxies appeared to be moving away from us. The farther the galaxy, the faster it seemed to be receding. This wasn't because we occupied some special place in the cosmos from which everything else was fleeing. Rather, it revealed that space itself was expanding uniformly in all directions, carrying galaxies along like raisins in rising bread dough. Tonight, as you rest under these apparently motionless stars, you're actually participating in this cosmic expansion. The atoms in your body, the air you breathe, The ground beneath you, all of it exists within expanding spacetime. The expansion is so gentle on local scales that molecular forces, gravitational attraction, and the fundamental forces holding matter together easily overpower it. You don't stretch as the universe expands, nor does the Earth, nor even our solar system or galaxy, but on the largest scales, across the vast distances between galaxy clusters, dark energy's influence becomes undeniable. What makes this mystery even more profound is how recently we discovered it. As you look up at stars that have shone for millions or billions of years, consider that humans have known about dark energy for less than 3 decades. The discovery came not from theoretical predictions, but from careful observations of distant exploding star supernovae so bright they can be seen across billions of light-years of space. These stellar explosions serve as cosmic lighthouses, their brightness so predictable that astronomers can use them to measure distances across the universe with remarkable precision. When scientists studied these distant supernovae in the 1990s, expecting to find evidence that cosmic expansion was gradually slowing down, they instead discovered something that revolutionized our understanding of reality itself. The expansion was accelerating, driven by this invisible, mysterious dark energy that permeates every corner of space. It's as if the universe has been holding its breath for billions of years and is now beginning to exhale, slowly but persistently, pushing everything apart with an influence so subtle yet so vast that it dwarfs all the matter and energy we can directly observe. As your eyes trace the familiar patterns of constellations overhead, you're seeing the universe caught between 2 great forces. Gravity tries to pull everything together, while dark energy gently but relentlessly pushes everything apart. For now, on the scales of stars and galaxies, gravity still dominates local regions. But on the largest scales, dark energy is winning, determining the ultimate fate of everything you see above you. The light from these stars carries more than just illumination, it carries information about the cosmic expansion, and in wavelengths and frequencies that tell the story of a universe in motion. Tomorrow night, when you look up at these same stars, they will appear identical to your eyes, but the space between our galaxy and distant ones will have grown imperceptibly larger, pushed outward by the mysterious energy that fills every void. Close your eyes for a moment and imagine holding a single photon of light in the palm of your hand. This tiny packet of energy, smaller than the smallest particle would ever imagine, has just completed an impossible journey. It left the surface of a distant star when the universe was younger, when galaxies were closer together, when the very fabric of space itself was more tightly woven than it is today. That photon has been traveling through expanding space for millions, perhaps billions of years. As it journeyed toward you, something remarkable happened, something so subtle yet profound that it revolutionized our understanding of the cosmos. The photon's wavelength, its very essence as light, was gently stretched by the expansion of space itself. What began as blue light might have become green. What started as green might have shifted to yellow, and yellow might have deepened into the warm glow of red. This stretching of light is called redshift, and it's written into every beam of starlight that crosses the universe. Imagine space as a vast, invisible ocean, and light waves as ripples moving across its surface. As the ocean itself expands, those ripples get stretched out, their peaks spread farther apart. The light doesn't lose energy by moving through space, rather, space itself grows larger around the light, pulling its wavelength longer like gentle hands stretching a spring. When you look up at the night sky, your eyes are collecting these traveled photons, each one carrying its own story of cosmic expansion. The nearest stars appear white or blue-white because their light reaches you relatively unchanged. The expansion of space are as such short cosmic distances is negligible. But peer deeper into space, toward more distant galaxies, and the redshift becomes unmistakable. The most distant galaxies we can observe are so redshifted that their visible light has been stretched all the way into infrared wavelengths, invisible to human eyes, but detectable by our most sensitive instruments. In the early 20th century, an astronomer named Edwin Hubble spent countless nights at Mount Wilson Observatory, carefully studying the light from distant galaxies. He was working with Henrietta Swan Leavitt's discoveries about variable stars' cosmic lighthouses, whose brightness fluctuates in predictable patterns, allowing astronomers to measure distances across space with unprecedented accuracy. Night after night, Hubble collected spectra of distant galaxies, spreading their light into component colors, like sunlight through a prism. What Hubble discovered changed everything. The more distant a galaxy appeared, the more its light was shifted toward the red end of the spectrum. This wasn't random, it followed a precise mathematical relationship. Galaxies twice as far away showed twice as much redshift. Galaxies 3 times more distant showed 3 times the redshift. The pattern was unmistakable and universal. The farther you looked into space, the faster galaxies appeared to be receding from us. But here's the beautiful paradox that reveals the true nature of cosmic expansion. This relationship holds true no matter where you are in the universe. If you could instantly transport yourself to one of those distant, redshifted galaxies, you would see our Milky Way galaxy redshifted by exactly the same amount. From that distant vantage point, it would appear that everything in the universe was racing away from you, just as everything appears to be racing away from us here on Earth. This isn't because we occupy some special position at the center of cosmic expansion. Rather, it reveals that expansion is happening uniformly throughout space. Every region of the universe is moving away from every other region. It's not that galaxies are flying through space like rockets, it's that space itself is growing, carrying galaxies along like boats on a river, where the river itself is constantly widening. Think of it this way: if you could paint dots on a balloon, and then inflate it slowly, each dot would appear to move away from every other dot, even though the dots themselves aren't moving across the balloon's surface. The balloon's expansion carries them apart. Similarly, galaxies aren't racing through space, space is expanding, carrying them along in a cosmic dance that's been unfolding for nearly 14 billion years. The light from the most distant observable galaxies left those stars when the universe was less than 1 billion years old, when the first generation of galaxies was just beginning to form. That ancient light has been traveling toward us ever since, its wavelength gradually stretched by billions of years of cosmic expansion. When it finally reaches our telescopes, it carries within its redshifted spectrum the entire history of the universe's growth. But redshift tells us even more than just that the universe is expanding. By carefully measuring how much the light from distant galaxies has been stretched, astronomers can calculate not only how fast the universe was expanding at different times in cosmic history, but also how that expansion rate has changed over time. This is where the story becomes truly extraordinary. For the first several billion years after the Big Bang, the expansion of the universe was indeed slowing down, just as you might expect. Gravity was gradually winning its tug-of-war against the initial explosive force that set expansion in motion. The mutual gravitational attraction of all matter in the universe was acting like a cosmic brake, steadily reducing the expansion rate. If this deceleration had continued, the universe might eventually have stopped expanding altogether, then begun to contract, ultimately collapsing back into a final big crunch. For decades, cosmologists debated whether the universe contained enough matter to halt expansion entirely, or whether it would continue expanding forever. But at an ever-decreasing rate, the light from distant supernovae exploding stars so bright they can be seen across billions of light years provided the key to resolving this cosmic question. These stellar explosions are remarkably consistent in their brightness, making them perfect cosmic measuring sticks. By comparing how bright they appear to how bright they should appear at their measured distances, astronomers can determine exactly how cosmic expansion has changed over time. As you rest here contemplating the night sky, consider that every photon entering your eyes is a messenger from the past, carrying information about the state of the universe when it began its journey. The light from Sirius left that star about 8.5 years ago. The light from more distant stars carries News that's decades, centuries, or millennia old, and the light from the most distant galaxies tells us about conditions in the universe when it was young and very different from today. This ancient light reveals something that nobody expected to find. Around 5 to 6 billion years ago, something remarkable happened to cosmic expansion. Instead of continuing to slow down under gravity's influence, the expansion began to accelerate. It was as if the universe suddenly shifted gears, transitioning from a gradual deceleration to an ever-increasing expansion rate that continues to this day. The photons reaching your eyes tonight carry this story written in their wavelengths. They've been stretched by billions of years of accelerating expansion. Their colors shifted toward red in precise proportion to the amount of cosmic growth they've witnessed. Each beam of starlight is both illumination and information, both beauty and scientific data, both present moment and cosmic history. The implications are staggering. Something must be driving this acceleration, some form of energy that opposes gravity's attractive force and pushes space apart. This mysterious influence, which we call dark energy, must constitute the majority of all energy in the universe, yet it reveals itself only through its gravitational effects on the largest scales, remaining invisible to every other form of detection. As your eyes adjust to the darkness and more stars become visible, you're seeing deeper into space and further back in time. That faint patch of light just visible at the edge of your vision might be the Andromeda Galaxy, our nearest large galactic neighbor. It's like carrying a journey of 2.5 million years. But even Andromeda is practically next door in cosmic terms, close enough that local gravitational forces overcome cosmic expansion, which is why Andromeda is actually moving toward us rather than away. The universe breathes outward on scales so vast that entire galaxy clusters drift apart like islands in an expanding ocean. Yet the expansion is so gentle that atoms remain bound, planets orbit stars, and galaxies hold together through their own gravity. Dark energy works only on the largest scales, where its subtle but persistent influence gradually overcomes all other forces, determining the ultimate fate of everything you see above you tonight. As you contemplate these traveling photons and their stories of cosmic expansion, you're witnessing the universe in the process of revealing one of its deepest secrets. The light itself becomes a library of cosmic history, each wavelength a chapter in the story of how space itself has grown and evolved. But what exactly is this space that stretches and grows, this stage upon which all cosmic drama unfolds? Settle back and let your mind drift beyond the familiar world of solid objects and empty air. Tonight, you're going to discover that space itself, the seemingly empty stage upon which all cosmic drama unfolds, is far from empty or passive. Space is dynamic, responsive, alive with possibilities that would have seemed like pure fantasy just over a century ago. Before Einstein, space was thought to be like a vast, invisible container, a fixed backdrop against which matter moved and events unfolded. Time was imagined as a steady river flowing at the same rate everywhere in the universe, unaffected by anything that happened within it. Space and time were separate, absolute, unchanging frameworks that existed independently of the matter and energy they contained. But Einstein revealed something far more beautiful and mysterious. Space and time are not separate entities at all. They're woven together into a single, unified fabric called spacetime. This fabric is not rigid like a container, but flexible like a vast cosmic membrane that can bend, stretch, ripple, and curve in response to the matter and energy it contains. Imagine you're lying on a soft, enormous trampoline that stretches beyond the horizon in all directions. This trampoline represents the fabric of spacetime. Now picture placing a bowling ball at the center of this cosmic trampoline. The heavy ball creates a depression, curving the fabric around it. If you roll a marble nearby, it doesn't travel in a straight line, it follows the curves created by the bowling ball's presence, spiraling around the depression, complete orbiting a star. This is how gravity works in Einstein's universe. Massive objects like stars and planets curve the fabric of space-time around them, and this curvature is what we experience as gravitational attraction. You're not being pulled toward the Earth by some mysterious force, you're following the natural curves in spacetime created by our planet's mass. The Moon orbits Earth not because a force reaches across empty space to grab it, but because Earth's mass curves spacetime in such a way that the Moon's natural path through that curved space becomes an orbit. The more massive an object, the more dramatically it curves spacetime. A star curves space more than a planet, and a black hole curves space so extremely that not even light can escape from its gravitational embrace. But every bit of matter and energy in the universe contributes to the overall curvature of spacetime. From the smallest particle to the largest galaxy cluster dot, now comes the truly remarkable part. This flexible fabric of spacetime can itself expand. When cosmologists talk about the universe expanding, they're not describing objects flying apart through static space. They're describing space itself growing larger, like our cosmic trampoline, being gently stretched in all directions simultaneously. The galaxies riding on this expanding fabric move apart, not because they're racing away from each other, but because the space between them is continuously growing. Picture our trampoline spacetime being slowly stretched by invisible hands at its edges. The bowling balls and marbles on its surface representing galaxies and stars don't move across the trampoline surface. Instead, they're carried apart as the trampoline itself expands. The distances between them increase not because they're moving through space, but because space itself is expanding. This expansion is incredibly gentle on small scales, the electromagnetic forces holding atoms together, the gravitational bonds between Earth and Moon, even the gravitational attraction holding our galaxy together. All these local forces easily overcome the expansion of space. You don't grow larger as the universe expands, nor does your house, or your planet, or even your solar system. The expansion becomes noticeable only on the vast scales between galaxy clusters, where no other forces are strong enough to resist it. But here's where our understanding takes another breathtaking turn. Einstein's equations describing the curvature of spacetime include a term that he initially considered unnecessary: the cosmological constant. This mathematical term represents the possibility that space itself possesses a kind of inherent energy, an energy that exists even in the complete absence of matter and radiation. Einstein originally added this term to his equations to balance the gravitational attraction of matter, keeping the universe static as he then believed it to be. When Hubble's observations revealed that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest mistake. He removed it from his equations, assuming that the observed expansion was simply the aftermath of the Big Bang gradually slowing down under gravity's influence. But the universe, as we've discovered, had other plans. The mysterious acceleration of cosmic expansion suggests that Einstein's mistake might actually have been one of physics' most profound insights. If the cosmological constant represents real energy inherent in space itself, then every cubic centimeter of seemingly empty space contributes a tiny amount of energy to the universe's total energy budget. This energy, dark energy, has a strange and wonderful property. Unlike matter, which becomes less dense as the universe expands and space grows larger, dark energy maintains constant density. As space expands, more space is created, and that new space comes equipped with the same dark energy density as the original space. It's as if our expanding trampoline somehow creates more trampoline material as it stretches, maintaining the same properties throughout. The implications are profound. In a universe where matter becomes increasingly diluted by expansion, while dark energy maintains constant density, dark energy will eventually dominate completely. This is already happening on the largest scales, where dark energy's influence has begun to overpower gravity's ability to hold galaxy clusters together. As you lie here contemplating the night sky, you're resting within this dynamic fabric of spacetime. Every breath you take, every heartbeat, every thought passing through your mind, all of it occurs within space that is subtly but continuously expanding. The expansion is so gentle on human scales that you experience spacetime as perfectly stable and reliable, Yet you're actually embedded in a cosmic fabric that has been growing for nearly 14 billion years. The light from distant stars that reaches your eyes tonight has traveled through this expanding spacetime, its wavelength stretched by the growth of the fabric through which it moved. Each photon carries information just about the star that emitted it, but about the history of spacetime expansion during its journey. The redshift of distant galaxies isn't just evidence of motion, it's a direct measurement of how much space has grown during the light's travel time. Einstein showed us that space and time are not the fixed stage we once imagined, but active participants in the cosmic drama. Spacetime bends around matter, guides the motion of objects, and even participates in the expansion of the universe itself. The fabric of reality is far more dynamic and responsive than our everyday experience suggests. Tonight, as you rest within this expanding fabric, you're witnessing one of the universe's most elegant dances. Matter and energy curve spacetime. Spacetime guides the motion of matter and energy, and the mysterious dark energy inherent in space itself drives the entire cosmic expansion. You're not just observing the universe, you're part of its fabric, embedded in the same spacetime that connects every star, galaxy, and cosmic structure across the observable universe. But this elegant dance of expansion wasn't always accelerating. For billions of years, cosmic expansion gradually slowed as gravity fought against the initial explosive force of the Big Bang. Then, something extraordinary happened that changed the course of cosmic evolution forever. Picture yourself standing in a quiet field at twilight, holding a ball in your hand. You throw it upward with all your strength, watching it rise against the pull of gravity. At first, the ball climbs quickly, but Earth's gravitational attraction gradually slows its ascent. Eventually, it reaches the peak of its arc, hangs motionless for an instant, then begins to fall back toward your waiting hands. This is exactly what astronomers expected to find when they looked deep into space to measure how cosmic expansion had changed over time. For decades, the prevailing wisdom seemed unshakable. The universe had begun with the explosive expansion of the Big Bang, and gravity had been working ever since to slow that expansion down. Just like your thrown ball, cosmic expansion should be gradually losing steam, decelerated by the gravitational attraction of all the matter scattered throughout space. The only question was whether the universe contained enough matter to eventually halt expansion entirely, causing everything to collapse back into a big crunch, or whether expansion would continue forever at an ever-decreasing rate. This wasn't merely theoretical speculation. By the 1990s, technology had advanced enough to measure cosmic expansion rates across different epochs of universal history. The key lay in studying Type Ia supernovae, the brilliant death explosions of certain white dwarf stars. These cosmic catastrophes are remarkable for their consistency. Each Type Ia supernova reaches nearly the same peak brightness, making them standard candles that astronomers can use to measure distances across billions of light years with unprecedented precision. The strategy was elegant in its simplicity. By comparing how bright these supernovae appeared in our telescopes to how bright they should appear at their measured distances, astronomers could determine exactly how much the universe had expanded during the light's journey from each exploding star to Earth. Supernovae in nearby galaxies would reveal recent expansion rates, while those in distant galaxies would show how fast the universe was expanding billions of years ago. When their light first began its journey toward us, to competing research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, embarked on this cosmic detective work in the mid-1990s. Both teams were racing to answer the same fundamental question: how much was cosmic expansion slowing down? They expected to measure the rate of deceleration and determine whether the universe would expand forever or eventually collapse, night after night. These astronomers scanned the skies with increasingly powerful telescopes, searching for the telltale signatures of distant supernovae. They developed sophisticated techniques for identifying these stellar explosions in galaxies billions of light years away, then carefully measured their brightness and redshift to map the expansion history of the universe. The work was painstaking, requiring years of observations and meticulous analysis to achieve the precision needed to detect subtle changes in expansion rates across cosmic time. As the data accumulated through the late 1990s, something extraordinary began to emerge from the numbers, something that contradicted every expectation and challenged our fundamental understanding of cosmic evolution. The distant supernovae were systematically fainter than they should have been if expansion was slowing down. This could mean only one thing: these stellar explosions were farther away than expected, which meant the universe homogene, and a detective called to investigate a crime scene where the perpetrator left no direct evidence, no fingerprints, no DNA, no witnesses. Yet everywhere you look, you find subtle signs of their presence. A chair moves slightly from its usual position, a book left open to a particular page, a cup of coffee still warm on the table. Through careful observation and deduction, you begin to construct a portrait of someone you have never seen, building understanding from the traces they left behind. This is precisely how astronomers have learned to map dark energy. They cannot observe it directly, cannot capture it in a jar or photograph it through a telescope. Instead, they have become cosmic detectives, reading the universe's story through the subtle signatures that dark energy's influence has written across space and time. The first and most dramatic clue came from dying stars in distant galaxies. Type Ia supernovae are among the most violent events in the cosmos, the explosive death throes of white dwarf stars that have grown too massive to support themselves. These stellar explosions are so bright they can outshine entire galaxies for weeks, becoming visible across billions of light-years of space. More importantly, they serve as cosmic lighthouses, each one releasing approximately the same amount of energy, allowing astronomers to use them as standard candles to measure cosmic distances. In the 1990s, two teams of astronomers began systematically studying these distant supernovae, expecting to measure how gravity was gradually slowing the universe's expansion. They prepared to quantify the cosmic deceleration, to map how the universe's expansion rate had decreased over billions of years. Instead, they discovered something that revolutionized our understanding of the cosmos. The distant supernovae appeared dimmer than expected, which meant they were farther away than anticipated, which meant the universe's expansion had been accelerating, not slowing down. Picture throwing a ball upward and watching it not only fail to slow down as gravity pulls on it, but actually speed up as it rises. This is what the supernova observations revealed about cosmic expansion. Something was counteracting gravity's pull, pushing space apart with increasing vigor. That something was dark energy, and its discovery earned the 2011 Nobel Prize in Physics. But supernovae were just the beginning of the detective work. The cosmic microwave background, the afterglow of the Big Bang itself, provides another crucial piece of evidence. This ancient light, stretched and cooled by nearly 14 billion years of cosmic expansion, carries within its subtle temperature variations a complete record of the universe's early structure. It's like finding a baby photograph of the cosmos, showing exactly how matter was distributed when the universe was only 380,000 years old. By comparing this primordial snapshot with the current distribution of galaxies, astronomers can trace how cosmic structure as Chapter 5. The invisible sculptor. You wake each morning to a world where the visible surrounds you, sunlight streaming through windows, trees swaying in the breeze, the solid ground beneath your feet. Yet tonight, as you settle into comfort, consider this: everything you can see, touch, and experience makes up less than 5% of the universe. The rest belongs to realms invisible, to forces that sculpt reality without ever revealing themselves directly to your senses. Imagine standing in a vast art gallery where most of the sculptures are made of glass so clear, so perfectly transparent, that you can only detect their presence by watching how they bend the light around them. This is your universe, a cosmic exhibition where the most powerful artist works exclusively with invisible materials. Dark energy is this unseen sculptor, composing with a medium that fills every corner of space. It doesn't announce itself with flashing lights or thunderous sounds. Instead, it works with the patience of geological time, the persistence of water shaping stone, the quiet determination of seeds growing in darkness. You might wonder how something invisible can be so certain to exist. The answer lies in watching the universe's grandest performance, its expansion. For decades, astronomers expected to find that gravity was slowly winning the cosmic tug-of-war, gradually pulling galaxies back together, slowing the expansion that began with the Big Bang. Instead, they discovered something extraordinary. The expansion is accelerating, picking up speed like a car whose driver has discovered a long, open highway. This acceleration requires energy, vast amounts of it, distributed uniformly throughout space. Picture a river flowing faster and faster downstream. Despite having no visible source of additional water, you would know something powerful was feeding that river, even if you couldn't see what it was. Dark energy is that invisible source, feeding the expansion of space itself. The numbers are staggering in their implications. If you could somehow weigh all the energy in the universe, dark energy would tip the scales at roughly 70% of the total. Dark matter, another invisible component, would account for about 25%. Everything else, every star, planet, galaxy, and cosmic gas cloud would barely register as a few percent of the cosmic inventory. Yet dark energy reveals itself through its effects with remarkable consistency. Wherever astronomers look, whether toward distant galaxies billions of light years away or in the space between nearby stars, they find the same signature: space itself expanding at an accelerating rate. It's as if the universe has discovered a font of eternal youth, growing more energetic with age rather than slowing down. This invisible sculptor works on scales that dwarf human imagination. While you sleep tonight, dark energy is gently stretching the fabric of space itself, creating more room between galaxies, pushing the boundaries of the observable universe ever outward. It operates not by adding things to space, but by adding space itself, new cubic meters of emptiness appearing constantly between existing matter. Think of dark energy as the universe's way of exhaling. With each breath, space expands slightly, creating room for new possibilities, new configurations of matter and energy. Unlike the air you breathe, which eventually runs out, this cosmic breath seems inexhaustible, powered by some deep property of space itself. The mystery deepens when you consider that dark energy appears to be remarkably uniform. Unlike matter, which clumps together to form stars and galaxies, dark energy maintains the same density everywhere. As space expands and creates more volume, more dark energy appears to fill it, maintaining perfect consistency across the cosmos. It's as if the universe has access to an unlimited account of this mysterious energy, drawing upon it to fund its ongoing expansion. Scientists have proposed various candidates for what dark energy might be. Perhaps it's the energy inherent in empty space itself, a kind of cosmic foam that bubbles with quantum activity. Maybe it's a new field, similar to the electromagnetic field, but operating on cosmological scales. Or it could be a sign that our understanding of gravity itself needs revision, that Einstein's equations require new terms to describe reality at the largest scales. What remains consistent across all these possibilities is dark energy's role. As the universe's primary architect, it doesn't build structures like gravity does, clustering matter into stars and galaxies. Instead, it creates the canvas upon which all cosmic architecture takes place. It provides the expanding stage for the grand drama of cosmic evolution. As you drift towards sleep, imagine yourself floating in this ocean of dark energy. You cannot feel it directly, but it surrounds you completely, more intimate than the air you breathe. Every cubic centimeter of space around you, including the space between the atoms in your body, contains this mysterious energy, participating in the universe's grand expansion. The remarkable thing is that you are witnessing this expansion happen in real time. Right now, as you read these words, the space between distant galaxies is growing. The universe is becoming a larger place, second by second, creating new room for future stars, future worlds, future possibilities. Dark energy is the invisible, handwriting the story of tomorrow across the cosmos. This expansion doesn't stretch you or your immediate surroundings, because gravity and the other fundamental forces easily overcome dark energy's influence at small scales. But step back to view the universe as a whole, and dark energy's artistry becomes unmistakable. It's painting on a canvas billions of light years across, using brushstrokes that span millions of years. The invisible sculptor works without ego, without signature, without any desire for recognition. It simply shapes, constantly and quietly, transforming the universe through the most subtle of touches. Its masterpiece is not any single object, but the very architecture of space and time itself, the expanding stage upon which every cosmic story unfolds. Tonight, as you settle into rest, you do so within this invisible energy field that permeates everything. You are held not just by gravity or the solid earth beneath you, but by the gentle, persistent force that sculpts the cosmos itself. And in the quantum whispers of empty space, other mysteries await discovery. Close your eyes and imagine the most perfect emptiness you can conceive, not the darkness behind your eyelids, not the quiet of a still room, but true nothingness, a volume of space from which every last atom has been removed, every photon extracted, every trace of matter and energy carefully swept away. You might think you have achieved perfect vacuum, absolute zero, the purest possible silence. Yet quantum mechanics whispers a different truth. Even here, in this supposed emptiness, the universe hums with ceaseless activity. This is the quantum vacuum, and it refuses to remain truly empty. Like a calm lake that appears perfectly still from a distance, but reveals gentle ripples when viewed closely. Empty space bubbles with constant motion of the smallest scales. Particles appear from nowhere and vanish almost instantly, borrowing energy from the universe's quantum bank account and repaying it so quickly that the books never quite balance, yet somehow never fall into debt. Picture standing in a snow globe just after someone has shaken it. The flakes swirl and dance in patterns that seem random yet follow hidden rules. Now imagine that the snowflakes are pairs of particles, an electron and its antimatter twin, a positron materializing from pure vacuum, existing for the briefest moment quantum mechanics allows, then annihilating each other and disappearing back into nothingness. This dance happens everywhere, constantly, in every cubic centimeter of space, including the seemingly empty areas between the atoms in your body. These quantum fluctuations are not theoretical curiosities. They produce measurable effects in our world. Between two metal plates placed very close together in a vacuum, fewer virtual particles can fit than in the open space beyond. This creates a tiny but real pressure difference, the Casimir effect, that actually pushes the plates together. Empty space, it turns out, has preferences, moods, and a kind of quantum personality that influences the behavior of matter. The energy associated with these quantum whispers might be related to dark energy itself. Some physicists propose that the vacuum energy of space, the sum total of all these fleeting particle pairs and quantum fluctuations, could be the mysterious force driving cosmic expansion. It's an elegant idea. The universe expands because space itself contains an inherent restlessness, a quantum impatience that prevents true stillness. Yet the mathematics of this connection presents one of the most profound puzzles in modern physics. When scientists calculate how much energy the quantum vacuum should contain, they arrive at a number so enormous it would tear the universe apart in the tiniest fraction of a second. The predicted vacuum energy exceeds the observed dark energy by a factor of 10,120, a discrepancy so vast it makes the difference between a grain of sand and the entire observable universe seem negligible. This enormous mismatch suggests that our understanding of either quantum mechanics or cosmology or both requires fundamental revision. Perhaps the quantum whispers in empty space are more subtle than we imagine. Maybe they don't contribute directly to dark energy, but instead reveal something deeper about the nature of space and time themselves. Consider the possibility that space is not the passive, empty stage we once imagined, but an active participant in the cosmic drama. Each point in space might possess its own quantum identity, its own relationship with the fundamental fields of nature. When space expands, it doesn't simply stretch like a rubber sheet. It creates new regions of quantum activity, new volumes of vacuum energy, new territories for virtual particles to explore. The quantum vacuum might be the universe's memory system, storing information about every interaction that has ever occurred. When an electron annihilates with a positron in the depths of space, the event might leave a subtle impression on the vacuum itself, a quantum echo that influences how space behaves in that region. Over cosmic time, these accumulated impressions could shape the large-scale structure of the universe, guiding how galaxies form and how space expands. This perspective transforms the quantum whispers from mere background noise into the universe's fundamental language. Every virtual particle pair that appears and disappears might be a letter in this cosmic alphabet, spelling out the laws of physics in a script we are only beginning to learn to read. Dark energy might not be a separate force at all, but simply our macroscopic experience of the universe's quantum conversation with itself. As you breathe in this moment, quantum fields are oscillating through your body. Virtual particles are materializing and vanishing in the space between your cells, and the vacuum itself is participating in the quiet symphony of your existence. You are not separate from these quantum whispers. You are immersed in them, shaped by them, part of the ongoing conversation between matter and the apparently empty space that surrounds it. The boundary between something and nothing becomes meaningless at quantum scales. A region of space that contains no particles still thrums with field fluctuations. What we call empty space is actually full of potential, pregnant with possibilities, ready to give birth to particles, antiparticles, and perhaps entire universes. Given the right conditions, this quantum fertility would be the key to understanding just dark energy, but the universe's remarkable creativity. How did complexity emerge from simplicity? How did the rich tapestry of cosmic structure arise from the smooth aftermath of the Big Bang? The answer might lie in these quantum whispers, these constant fluctuations that prevent the universe from ever achieving perfect uniformity, perfect stillness, perfect emptiness. The vacuum's quantum activity occurs on timescales so brief they defy human intuition. A virtual particle pair might exist for only 10 to 21 seconds a duration that makes the blink of an eye seem geological. Yet in that inconceivably brief existence, they can influence the behavior of real particles, contribute to electromagnetic forces, and participate in the quantum processes that govern atomic interactions. Perhaps consciousness itself arises from these quantum whispers. Some researchers propose that the brain's microtubules, tiny structures within neurons, might be sensitive to quantum effects in the vacuum around them. If this is true, then your thoughts and dreams might be shaped by the same quantum fluctuations that fill empty space, connecting your inner experience to the universe's deepest level of activity. Tonight, as you prepare for sleep, remember that the quiet darkness around you is not empty, but alive with quantum conversation. Every cubic centimeter of space whispers with virtual particles, field fluctuations, and possibilities waiting to unfold. You rest within a universe that never truly rests, supported by an emptiness that is actually fullness, surrounded by a silence that is actually song. These quantum whispers might hold the key to mysteries we have not yet learned to ask about. In the marriage of quantum mechanics and cosmology, in the dance between the very small and the very large, profound equations await discovery. In 1917, Albert Einstein sat at his desk, wrestling with equations that describe the entire universe. His general theory of relativity had given him the mathematical tools to understand gravity, not as a force, but as the curvature of spacetime itself. Yet, when he applied these equations to the cosmos as a whole, they predicted something that seemed impossible. The universe could not remain static. It must be either expanding or contracting, growing larger or collapsing under its own gravitational weight. This troubled Einstein deeply. Like most scientists of his era, he believed the universe was eternal and unchanging, a vast, stable island of stars suspended in infinite space. To prevent his equations from predicting cosmic expansion or collapse, he added a new term, the cosmological constant, represented by the Greek letter lambda. This mathematical device would provide just enough repulsive force to balance gravity's attractive pull, allowing the universe to remain perfectly static. Imagine balancing a pencil on its point. Without constant adjustment, it will inevitably fall in one direction or another. Einstein's cosmological constant was like an invisible hand making those tiny corrections, keeping the cosmic pencil balanced upright for eternity. It was an elegant, mathematical solution to preserve the eternal universe that fit his philosophical expectations. Yet this solution came with a price. The cosmological constant represented a new kind of energy that filled all of space uniformly, not concentrated in stars or galaxies, but spread evenly throughout the vacuum itself. This vacuum energy would need to maintain exactly the right density to balance gravity precisely, neither too strong nor too weak, calibrated to cosmic perfection across all of space and time. When Edwin Hubble's observations in the 1920s revealed that distant galaxies were indeed moving away from us, proving that the universe was expanding, Einstein famously called the cosmological constant his greatest mistake. The universe didn't need to be held static after all. It was naturally dynamic, growing, evolving. The elegant balance Einstein had tried to engineer was not only unnecessary, but had prevented him from predicting one of the most important discoveries in cosmology. For decades, most physicists followed Einstein's lead and set the cosmological constant to zero. The expanding universe could be understood through gravity and the initial conditions of the Big Bang alone. The vacuum energy that Einstein had invented to stabilize the cosmos seemed to have no place in the real, dynamic universe that observations revealed, but the universe, as it often does, had the last laugh. In the 1990s, astronomers studying distant supernovae made a shocking discovery. Not only was the universe expanding, but its expansion was accelerating. Something was pushing space apart with ever-increasing vigor, overcoming gravity's attempts to slow the expansion down. Einstein's mistake suddenly looked like prophetic insight. The equations that emerged from these observations looked remarkably similar to Einstein's original formulation, complete with a cosmological constant term. But now, instead of being a mathematical convenience to enforce stasis, lambda represented something real and active in the universe, dark energy. The very term Einstein had introduced to prevent cosmic change had become the mechanism driving the universe's accelerating transformation. This resurrection of the cosmological constant creates both satisfaction and mystery. The mathematical elegance is undeniable. Einstein's century-old equations, with minimal modification, can describe the accelerating expansion that astronomers observe today. Yet the physical meaning of lambda remains as enigmatic as ever. What is this energy that fills every cubic centimeter of space? Why does it have exactly the density required to drive cosmic acceleration? The cosmological constant implies that empty space itself possesses energy. This isn't energy stored in particles or fields in the traditional sense, but rather an intrinsic property of spacetime. As the universe expands and creates more space, it creates more dark energy, maintaining the same density everywhere while increasing the total amount of cosmic acceleration. It's as if space comes preloaded with expansive energy, a built-in tendency to grow. Modern measurements suggest that the cosmological constant has a value of approximately 1029 grams per cubic centimeter, an almost inconceivably small number. To put this in perspective, if you could weigh a volume of space, the size of your bedroom, its dark energy would have the mass of about 1/10 of a hydrogen atom. Yet this tiny density, multiplied across the entire observable universe, dominates the cosmic energy budget and determines the universe's ultimate fate. the precision required for this value creates what physicists call the cosmological constant problem. If the vacuum energy came from quantum fluctuations, as some theories suggest, it should be vastly larger, so large that the universe would have torn itself apart long before stars or galaxies could form. The fact that the cosmological constant has just the right value to permit complexity and life to emerge seems to require an extraordinary fine-tuning that makes physicists uncomfortable. Some propose that the cosmological constant we observe is the result of a cosmic coincidence, that enormous positive and negative contributions to vacuum energy almost perfectly cancel out, leaving behind the tiny residue we call dark energy. This explanation feels unsatisfying, like balancing a massive equation, only to discover that the most important term is determined by an accidental rounding error in the 29th decimal place. Others suggest that the cosmological constant isn't truly constant at all, but varies slowly with time or position in ways too subtle for current observations to detect. This possibility opens new theoretical territories where dark energy might have been different in the early universe, or might change as cosmic expansion continues. The lambda in Einstein's equations might be more like a slowly evolving field than a fixed number written into the fabric of spacet. The cosmological constant also raises profound questions about the nature of space itself. If empty space has energy, what happens to energy conservation as the universe expands? As space creates more of itself, does it violate the principle that energy cannot be created or destroyed? Or does the expansion of space itself provide the mechanism through which vacuum energy increases, maintaining its density while growing in total amount? These questions touch the deepest foundations of physics. Einstein's equations describe how matter and energy curve spacetime, but they assume that spacetime itself is simply the stage upon which physical processes occur. The cosmological constant suggests that spacetime is also an actor, contributing its own energy to the cosmic drama and influencing its own evolution. Perhaps the most remarkable aspect of the cosmological constant is how it connects Einstein's purely theoretical concerns with the observational reality of today's cosmology. The term he added reluctantly to preserve his philosophical preconceptions about an eternal universe has become central to understanding a dynamic, accelerating cosmos that he never imagined. As you rest tonight, consider that the space around you, the seemingly empty regions between atoms, between planets, between stars, carries within it the subtle energy that determines the universe's destiny. Einstein's lambda permeates your bedroom, your body, every cubic millimeter of the cosmos. It's the quietest force in nature, yet it shapes the grandest possible scales of space and time. The cosmic equation continues to evolve as new observations refine our understanding of dark energy's properties. But somewhere in the mathematical symphony that Einstein composed over a century ago, the notes that describe our accelerating universe were already written, waiting for astronomers to develop instruments sensitive enough to hear their subtle cosmic song. You find yourself standing at the edge of time itself, looking forward into a future so distant that the very concept of years becomes meaningless. Trillions upon trillions of years stretch before you like an endless ocean, and in this vast expanse of time, you can see the gentle but inexorable work of dark energy painting the universe's final chapters. Imagine, if you will, that you are watching the universe from a place outside of time, where eons pass like seasons in a year. You see dark energy continuing its patient work, stretching space with the same quiet persistence that moves continents across Earth's surface. But unlike the geological changes you know, this stretching never pauses, never reverses, never rests. In the first act of this cosmic future, you witness what astronomers call the age of isolation. Galaxies that now dance together in clusters, held by gravity's embrace, begin to drift apart like leaves on an expanding pond. The Milky Way and Andromeda, destined to merge in a few billion years, will eventually find themselves alone again, floating in an ocean of ever-growing emptiness. Picture our own galaxy as it will exist in this far future, a single island of stars in a sea of darkness so vast that light from other galaxies can no longer reach us. The night sky, which now sparkles with the combined light of billions of distant galaxies, will grow darker and darker until only our own stars remain visible. It's as if the universe is slowly drawing curtains across the cosmic stage, leaving each galaxy to perform its final act in solitude. But this isolation brings its own strange beauty. Without the gravitational interference from neighboring galaxies, the Milky Way will settle into a perfect spiral, its arms rotating with the precision of a celestial clock. Stars will continue to be born from the remaining gas and dust, though more slowly now. Like the last flowers blooming in an autumn garden. You watch as these future suns live out their lives in this quiet galaxy. The most massive stars will burn bright and fast, exploding in supernovas that briefly illuminate the cosmic darkness. Medium-sized stars like our Sun will swell into red giants before gently puffing off their outer layers, leaving behind white dwarf stars, cosmic embers that will glow for trillions of years. The smallest stars, the red dwarfs, will become the universe's great survivors. These dim, patient suns will burn their hydrogen fuel so slowly that they could shine for tens of trillions of years longer than the universe has currently existed. In this future darkness, they will be like lighthouse beacons, providing the last warmth and light in an increasingly cold cosmos. As you peer even further into time's depths, you see that even these red dwarf stars must eventually exhaust their fuel. One by one, they will fade to brown dwarfs, then to black dwarfs, gold, dark objects floating through space like cosmic ghosts. The age of stars will give way to the age of stellar remnants, white dwarfs, neutron stars, and black holes drifting through the expanding darkness. But the universe's expansion continues its relentless work. Space itself grows larger and larger, carrying these stellar remnants away from each other, like dust motes in an ever-expanding balloon. What was once a galaxy becomes a scattered collection of dark objects, each one isolated in its own patch of empty space. Yet even in this seeming desolation, you find something profoundly peaceful. There is no violence in this cosmic ending, no catastrophic collapse or fiery destruction. Instead, there is a gentle fading, like a song that slowly grows quieter until it becomes silence. The universe is not dying dramatically, it is simply spreading itself so thin that energy can no longer concentrate enough to create the dramatic events of cosmic youth. In this far future, you witness what physicists call heat death, not a burning, but a cooling. All energy becomes evenly distributed across the vast expanse of space, like warmth from a fire spreading throughout a room until every corner holds the same temperature. There are no more temperature differences to drive the engines of change, no more concentrations of energy to birth new stars or power the dance of planets. But in contemplating this distant future, you discover something unexpected, a deep sense of acceptance and even gratitude. This cosmic ending is not a failure or a tragedy. It is the natural completion of a story that began with the Big Bang. The universe is like a vast piece of music that starts with a dramatic crescendo and slowly, beautifully, fades to silence. Every star that will ever shine, every planet that will ever form, every moment of complexity and beauty that will ever exist, all of it unfolds in the vast middle movement of this cosmic symphony. You are living within that movement right now, surrounded by the universe at its most vibrant and creative phase. The knowledge that this cosmic story has an ending doesn't diminish its beauty, it enhances it. Every sunrise becomes more precious. When you understand that there will be a finite number of sunrises in the universe's history, every moment of warmth, every spark of life, every flash of consciousness becomes a rare and wonderful gift in a cosmos that will eventually grow cold and dark. As you stand at this edge of time, looking into the universe's distant future, you feel a profound connection to the present moment. The same dark energy that will eventually isolate galaxies is working right now, creating the space in which your life unfolds. The expansion of the universe is not something happening to you, it is something you are participating in, moment by moment, breath by breath. In this cosmic perspective, you begin to understand that impermanence is not the enemy of meaning, it is the source of meaning. The temporary nature of stars, galaxies, and even the universe itself doesn't make them less significant. It makes every moment they exist infinitely precious. You feel yourself settling into this understanding, inking into a warm bath. The future expansion of the universe, far from being frightening, becomes a reminder to cherish the cosmic moment you inhabit. In a universe destined for such quiet isolation, the fact that you exist now, surrounded by 10 billion galaxies blazing with starlight, feels like the most extraordinary gift imaginable. And as you contemplate this vast future written in expansion, you begin to wonder about your own place in this cosmic story, how the atoms that make up your body, forged in the hearts of dying stars, connect you to both the universe's ancient past and its distant future. Here, you are, lying in the quiet comfort of your bed, and yet you are simultaneously hurtling through space at tremendous speeds, riding on a planet that spins at over 1,000 miles per hour, while orbiting a star at 67,000 miles per hour, in a galaxy racing through the universe at hundreds of thousands of miles per hour. You are part of the grandest dance ever choreographed, and you have never stopped moving for a single moment of your existence. But there is something even more profound about your place in this cosmic story than motion alone. You are not simply an observer of the universe's expansion, you are made of the very same space-time that dark energy stretches, the space between the atoms in your body, the space between the particles that make up those atoms. All of it participates in the universe's gentle, eternal expansion. Think of your body as a constellation of ancient starlight made solid. The calcium in your bones was forged in the nuclear furnaces of massive stars that lived and died billions of years ago. The iron in your blood was created in the final, violent moments of a star's death in the supernova explosion that scattered these precious elements across space, like seeds on cosmic wind. The carbon that forms the backbone of every molecule in your body was crafted in the hearts of red giant stars, slowly built up atom by atom through nuclear fusion processes, so intricate they rival the most complex music ever composed. The oxygen you breathe was born in stars at least twice the mass of our sun, created when these stellar giants fused lighter elements together in the incredible heat and pressure of their cores. Even the hydrogen in your body, the most abundant element in your physical being, carries a story that reaches back to the universe's very beginning. This hydrogen was forged not in stars, but in the first few minutes after the Big Bang, when the cosmos was still so hot and dense that atomic nuclei could form directly from the primordial fire of creation. You are, quite literally, made of ancient light transformed into matter, held together by forces that have been operating since the universe's birth. The electromagnetic force that binds electrons to atomic nuclei in your body is the same force that creates the aurora dancing in Earth's polar skies. The strong nuclear force that holds the protons and neutrons together in your atom's cores is the same force that powers the sun and every star you see at night. But your connection to cosmic expansion goes deeper still. The space that exists between the cells in your body, between the molecules in those cells, between the atoms in those molecules, all of this space participates in the same expansion, driven by dark energy. You are not separate from the expanding universe. You are woven into its very fabric. As you lie here, dark energy is at work in the vast spaces between galaxies, gently stretching the cosmos and creating room for new possibilities. That same mysterious force influences the space-time around you, though on scales so small and with such weakness that other forces, gravity, electromagnetism, easily overwhelm its effects within your body and even within our solar system. Yet, the principle remains beautifully constant. You exist within the same space-time continuum that connects you to the most distant galaxies. The geometry of space around your body follows the same fundamental rules that govern the expansion of the entire universe. You are not just living in the cosmos, you are an expression of the cosmos, a way the universe has organized itself to become aware of its own existence. Consider this remarkable fact. The atoms in your left hand were likely forged in a completely different star than the atoms in your right hand. The calcium in one bone may have been created in a red giant that died 8 billion years ago, while the calcium in another bone came from a different star that exploded just 4 billion years ago. You are quite literally made of stardust from across the galaxy, gathered together by gravity and chemistry into the intricate pattern that is your physical existence. But you are more than just a collection of recycled stellar material. You are matter organized in such a way that the universe can contemplate itself. Through your consciousness, the cosmos has developed eyes to see its own beauty, a mind to ponder its own mysteries, and a heart to feel wonder at its own grandeur. When you look up at the night sky and feel the sight of distant stars, you are experiencing the universe appreciating itself. When you feel curiosity about dark energy and cosmic expansion, you are participating in the cosmos' attempt to understand its own nature. The questions that arise in your mind about the universe's fate are the universe asking these questions about itself through you. This perspective transforms your relationship with cosmic expansion from something happening around you to something you are intimately part of, the same creative force that drove cosmic inflation in the universe's first moments, that now manifests as dark energy stretching space between galaxies, is the force that created the stage upon which your life unfolds. Your thoughts themselves arise from electrochemical processes that depend on the fundamental forces woven into spacetime's fabric. Your capacity for love, wonder, and understanding emerges from the same physical laws that govern the birth and death of stars. You are not separate from the cosmic story, you are one of its most remarkable chapters. And what a chapter you are! In a universe that began as a hot, dense point and will eventually spread into cold, dark isolation, you represent an extraordinary flowering of complexity and consciousness. You exist during the universe's most creative epoch, when stars are actively forming, when planets can support life, when matter can organize itself into forms complex enough to think and feel and dream. Your ability to contemplate the universe's expansion, to feel both wonder and melancholy at its distant future, makes you a participant in one of the cosmos' greatest achievements, the emergence of awareness from matter, meaning from mechanism, love from the dance of particles and forces. As you settle deeper into rest, you can feel this connection viscerally. With each breath, you exchange atoms with the atmosphere around you, which exchanges atoms with the broader environment, which participates in the planetary cycles that connect Earth to the Sun, which moves through a galaxy that dances with dark energy across cosmic space. You are not a separate being observing the universe from the outside. You are the universe experiencing itself from the inside, a focal point where cosmic evolution has become conscious of its own unfolding. In understanding dark energy and expansion, you are participating in the cosmos journey towards self-knowledge. In this recognition, you find a peace deeper than any conventional comfort. You are exactly where you belong, not just on this planet, in this solar system, in this galaxy, but in this moment of cosmic time when the universe is complex enough, stable enough, and vast enough to support your existence and your wonder. The expanding universe cradles you not as a stranger, but as its own beloved child, born from its substance, shaped by its laws, and destined to return your atoms to the cosmic cycle when your individual dance is complete. You rest now in the embrace of the cosmos itself, held by the same spacetime that connects you to every star, every galaxy, and every moment of the universe's magnificent, expanding story.